Hi, this is a lesson on parametric first-order derivatives. And what we mean by first order is basically like a first derivative, but in parametrics, because there are multiple variables, we can consider different things to be first order or first derivatives, first order derivatives or first derivatives. So we could take dx dt, or the derivative of x with respect to t. We could take the derivative of y with respect to t. We can also consider slope, or dy dx, in sort of the more traditional first derivative fashion. So as a warm-up, I would like you to take a look at your packet. Depending on if you're looking at the labels that are written at the bottom of the pages or the PDF and the way that it's labeled electronically, it's page 7 or page 9, but it looks like this that I have on my screen here. And I'd like you to, in just a second, pause this video, take no more than 5 minutes by yourself. So if it tops out at 5 minutes, and you're not done, come back. But I would like you to try the 5 questions at the top of the page. And you will see that the same 5 questions are listed later on that page. You just want to look at the first set. And what I'm asking you to do here, as the arrows indicate, are to convert this first to Cartesian coordinates. Cartesian coordinates are those found credited to Rene Descartes, which is why they're called Cartesian, and they are just our regular XY coordinates. So you would do this in this particular situation by thinking about trig identities that you know. So in particular, in this problem, we're given that x is cosine of t and y is sine of t. So I would encourage you to remember that this is an identity that you know, and utilize that. And then when you're asked to find slope, remember that slope is dy dx. Okay, that is slope. All right, come back in 5 minutes and just do the best you can, and we'll see where you are. Okay, thank you for trying that yourself. That's a way to make sure that you're understanding things. All right, so we started out by discussing that you would use a trig identity, and so if cosine squared plus sine squared is 1, in this case, since cosine and sine are given to be x and y, that would be equivalent in Cartesian coordinates to saying x squared plus y squared equals 1. If you think about that with your geometry brain, you know that this is actually just this graph over here, right? This is just referring to the infamous unit circle, right? This is an equation of a circle centered at 0, radius 1. So question 1 said to find the slope when t equals 0. If I were to substitute in 0 for the t value in these two equations, in this pair of parametric equations, then I am going to get the coordinates of x equals 1 and y equals 0. And that, located on this circle, is over here, and at that point, the slope of my tangent line, which is what slope on a curve means, the slope of the tangent line at that point, that slope is undefined because the tangent line is a vertical line. Now, that is not the only such way that you could have come to that conclusion, and I will demonstrate a different way by showing you what I did for number 2. In question number 2, I realized that when I am at pi over 6, that gives me the coordinates of root 3 over 2 and a half. Again, I would just substitute in my value of the parameter that they gave me. They told me that t was pi over 6. I could substitute in that t value, or that parameter value, to get the coordinates of x and y. This part over here in my writing is from looking at my Cartesian equation and using implicit differentiation. Remember that we want to think of, in our Cartesian system, we're thinking of x as our independent variable and y as our dependent variable, dependent upon x, so that when I'm taking the derivative with respect to x, I need to remember to use chain rule right there. Okay, on the previous term, technically you could write dx over dx, but that doesn't really matter. That's going to be 1. The rate of change with x with respect to x will be at a rate of 1. And then you can isolate the dy dx in that expression that I put the red box around over here, and get that you have the opposite of x over y to get the slope, or the dy dx, and that is negative root 3. This should make sense as far as the geometry of the situation, or the trig of the situation. This is pi over 6, and so roughly, and this line is the tangent line, and that tangent line has a slope of negative root 3. Okay, same idea now at pi over 2, but actually kind of easier. Pi over 2 is located here. That tangent line is horizontal. If I recognize that, then I can save myself a lot of the calculation effort and just say that the slope is 0. But you also could use the same technique as I did in number 2. Where are the horizontal tangents? Well, we could actually go back to this equation here and make an equation for slope using our parametric equation, if we wanted. Everything is going to work. Like if you do valid math, there's lots of ways to do some of these questions, multiple ways, I should say, maybe not lots, but there are multiple ways to do all these questions. And so if you did it a different way, that's okay. All right, but here is an expression for slope in terms of our parameter t. So if I want to know where my horizontal tangents are, I want to know where slope, and slope is dy dx, where slope is 0. And so if I need this expression to be 0, I need the numerator to be 0, while the denominator is not 0. So I need cosine of t to be 0, which is going to happen, if you think of your unit circle, right here and right here, as I go around and around. So that would be at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. Okay? And then the next question was, where are the vertical tangents? There's going to be vertical tangents at exactly the other places, right, that I didn't just name. So we were talking about the top and the bottom of the unit circle. So over here and over here are going to be where my vertical tangents are. I can see that computationally because I would want this bottom part to be 0. Vertical means undefined slope. Undefined slope means that this slope expression, dy dx, has something over here that is not a defined number, which would mean this bottom part would be like dividing by 0. So that's going to be our multiples of pi, right? 0, pi, 2 pi, 3 pi, blah, blah, okay? So that was all very fun. Here is a question that is one of those teacher questions. It's not really a question. Do you know what I'm saying? That was another one of them. How about that? It's like very meta. Okay, so what will this series of questions be like for increasingly more complex parametrics? Right? Like this is barely more complicated looking, but it's going to be worse, right? Because I can't just think about the unit circle. It's going to be like, I don't know what it's going to be like, some kind of loop-de-loop thing. I don't know. So is going to rectangular form always optimal, right? Like in this question, we relied on switching things to x and y and thinking about that. This is the teacher question I was talking about. It's not really a question. Is going to rectangular form always optimal? No, obviously not, because this is a whole unit on parametrics. Why would we have a whole unit on parametrics if we could just switch to rectangular and be happy? So the middle of the page, if you're looking at the PDF of notes, has a key idea for us, okay? And that key idea is based on chain rule, okay? So for chain rule, I don't know if you realize the reason it's called chain rule, but the reason it's called chain rule is more clear if you use specific notation. And so the notation I'm using here is what is credited to Leibniz. It's Leibniz notation, and that means the derivative of y with respect to x. Now, just a little point of math history. Newton, oh my gosh, Newton, I love so much of what you did, but this was crazy. Newton, when he first started working with derivatives, used this notation, this dot thing. Okay, so he would write like y with a dot on top if he wanted the derivative of y. And first of all, dots, like you think those little prime things are hard to keep track of. Also, I believe credited to Newton historically. I might be wrong on that, but I think so. But you think those little primes are hard to keep track of. The dot thing, like seriously, is hard to keep track of. And it has a serious disadvantage. Think in the back of your mind about what the disadvantage might be. Okay. Oh, actually, you know what? It's not Newton who's credited with the primes. It's Lagrange. I apologize to Lagrange. Lagrange, you're the one who came up with the primes. Newton had the dots. It's Leibniz, my dear. Leibniz who came up with this. And this is why Leibniz has my love. Honestly, it's this notation. Because the advantage of Leibniz notation, even though it's more writing, is that it denotes what we're taking the derivative with respect to. And in problems where you have multiple variables, that is actually kind of not something to gloss over, Newton or Lagrange. Come on, man. And just as another note, Euler, who I actually seriously love, don't tell the professor, had notation like this. Like, what are you doing, my dude, right? It's just kind of awkward, clunky, I don't know. So Leibniz, although sometimes thought of as more like a secondary founder of calculus, really helped to convey the ideas that Newton wasn't really communicating well. Okay, so that was all a side note about notation. Really, I want to talk to you about chain rule. So chain rule, you can see what chain rule is all about. If you say, well, the derivative of y with respect to x could be found like if you had a nested function, right? Like y, a function y that has u inside of it. So an example of that would be something like this. Here's my function u, and here's my outer function here, okay? And so y has is dependent on x, but it is like, there's like a composition, okay? So if you write chain rule using Leibniz notation, you can see the chain. This is the link in the chain, okay? And if we were to take that and rearrange it, we're going to find out how to deal with derivatives in the parametric life. So we can just rewrite this chain rule using different variables. So think of t as my independent variable now instead of x, and write this chain rule again, just using different letters in different slots. It's the same rule, okay? And then take this equation here and isolate the dy dx. So dy dx always is going to mean slope in terms of our Cartesian coordinate, right? It's the rate of the vertical change as compared to the horizontal change. That is exactly what slope is, right? Back in like 7th grade or whatever, you write like slope is y2 minus y1 over x2 minus x1. Oops, I just wrote a y for some reason. Okay, which is the same as saying change in y over change in x. Hello, that's calculus, okay? So that's the definition of slope in the Cartesian plane. If we isolate now for the dy dx, wow, I'm writing all over the place. If we isolate for the dy dx, we're going to have dy dt divided by dx dt. And that's how you find slope, staying in parametrics without going over to the Cartesian life. Okay, so the same 5 questions are printed at the bottom of the page. I would like you to not go over to the Cartesian world. Stay in parametric world. Utilize what is there directly, staying in parametrics, thinking in parametrics, okay? This thing I have circled in the corner, you're going to use that, okay? Because that's what slope is. And then think about horizontal and vertical. So, I'll actually give you a hint. Horizontal tangents means we want this slope to be 0. So that just means the top is 0. So that just means I need dy dt to be 0. What does a vertical tangent mean then? Vertical means slope is undefined, so I want the bottom to be 0. Okay, so now understand that each of these has the caveat that we want, the top to be 0 without the bottom being 0, or the bottom being 0 without the top being 0, because 0 over 0 is a whole different ball of wax, okay? So just understand that I'm simplifying a skosh there, okay? All right, hit it, try it, pause, and come back. Don't just keep listening. That's cheating. You're cheating yourself with the experience. The way to get good at math is to practice it yourself. Okay, so time to pause, time to try these in parametric, right, then come back. Okay, so I'm going to start out with the parametric that was given. Hopefully what you did was to say, okay, so if x is cosine of t, take the derivative of x with respect to t using my beautiful Leibniz notation. I know the derivative of cosine is negative sign. So that's that. And then the derivative of y with respect to t, derivative of sine is cosine. Okay, so here are the two facts that I'm going to use. If I take the division of those, I get what's up here. That's my slope. So this is the rate of change in the graph as we move through the graph. How is the horizontal component changing? This is as we move through the graph, as time ticks away, how is the vertical component changing? And this is slope. Okay, rate of change in x, rate of change in y, and slope. Okay, just to make sure you have context. Then we just do all these questions, right? Find the slope of the tangent at t equals blank. This is now super easy because look, we've got slope versus time. Right there, we can just plug in, because these are all values of t. Boom. Horizontal tangents are going to be where my slope, or my part that I highlighted blue, is equal to 0, just like we did up above. So I didn't rewrite that because we already did it. And so it's like the pi over 2, 3 pi over 2, 5 pi over 2. And the vertical tangent is going to be where the yellow highlighted part up here is equal to 0. So that's at your multiples of pi. Okay? Ta-da! So I do think that that ends up being a little more streamlined, which is good. Okay, it's about time for you to pause and try another thing. So on the next page, there is this problem. It has, it's an example, it has 7 pieces to it. I just want you to do numbers 1 through 5. We'll talk about 6 and 7 together. But I'd like you to pause, and this is the same kind of problem. Stay in parametric. Use your new skills. Remember how dy dx, gosh, tongue-tied. Dy dx is dy dt over dx dt. So find those separate derivatives and then just put them in a quotient. And then go ahead and find the things that are requested. Pause and come back. Okay, let's check your answers. So off to the side here, we have the calculation of dy dt, dx dt, and then take the quotient of those two. Okay, remember to put the dy dt on the top, dx dt on the bottom. I did simplify a little, just reducing the fraction, whatever, it doesn't matter if you don't, okay? Then it's just a matter of substituting in each of these values into that equation, okay? So you should get undefined, the equivalent of root 3 over 6, and 0, okay? Plug and check. 4 and 5 sometimes cause people a little bit more pause, so my thinking on each of these starts out in the margin. So if I'm looking for a horizontal tangent, that means I'm looking for slope to be 0. And if slope is 0, remember that slope, dy dx, is actually dy dt over dx dt. So if that has to equal 0, or 0 over 1, or 0 over any number that isn't 0, it's that this top part has to be 0. So in other words, I want to set my dy dt expression equal to 0, and dy dt set equal to 0. It means that cosine has to be 0, and that happens at the odd multiples of pi over 2, the top and the bottom of my unit circle. Question 5, I'm asked to find vertical tangents, and my vertical tangents are going to be when my slope is undefined. And slope is dy dt over dx dt. So for that to come out with something undefined, I need to have a non-zero number over 0. So this part has to be 0. So if dx dt is 0, the 1/3 doesn't matter. I just need to have the sine of 3t equal to 0. So I'm going to have, the 3 doesn't, the negative 6 doesn't matter, I meant to say, sorry, I said the wrong number there. The negative 6 doesn't matter, so because negative 6 can't be 0. So sine of 3t has to be 0, and that's going to happen at multiples of pi over 3. All right. The bottom 2 questions reference big ideas, okay? When is the particle moving to the right? So the particle would be moving to the right. My horizontal motion is measured by the rate of change in x as time passes. Right and left motion is this way, and that's my x variable. And moving to the right is denoted by dx dt being positive. So in this case, dx dt is negative 6 sine of 3t. I want that to be positive. Okay, we're going to come back to solving that in just a second. We're going to use our calculators. All right, and then when is the particle moving up? Well, up and down motion is a rate of change in my y-coordinate, and dy dt in this problem is 2 cosine of t. Moving up is denoted positively, whereas moving down would be when dy dt is negative. So these are the 2 inequalities that I want to look at. Now I have a little reminder here that we're going to look at the calculator next, and we're going to talk about a few things. We're going to talk about window, we're going to talk about ball and chain, my own name, and we're going to notice the calculate menu, okay? So take a second, go get your calculator, and come back. Okay, so in your calculator, you can see right here, the red button that is shown right here is the mode key. And notice that I have radian measurement for my angles, and I switched over to parametrics. Now, I'm actually not going to use parametrics to do this problem, but I wanted to talk to you about a couple things. So if I were to now just hit to the graph, well, actually, let me go to y equals. In y equals, notice I have x and y. They are both denoted with a little t to remind me that my independent variable is t. Okay, so I put in my x in terms of t, my y in terms of t in this problem. Now, if I just hit graph right now, it looks really, really weird, okay? And that is because window is very important. It's important in general, but it's really important when we're working in parametrics or later in the year when we're working in polar. So we want to make sure that the value of t encompasses enough values that we get a more complete picture of what's going on. So I'm going to say maybe 2 pi, since it's based on trig function, 0 to 2 pi seems like a pretty good shot. And then I might even want to make this a little bit smaller. And see, because that is, remember that the calculator actually doesn't know math, and so what it does is it plots dots, and then it will connect the dots. So the smaller your t-step, the more points the calculator will plot, and the better your graph will look in terms of accuracy. Okay, so that's the thing. If I want to see that more clearly, I could change my max and min for x and y, right? That was kind of small in the middle of my space there. So instead of going negative 10 to 10, I'm going negative 5 to 5. It's a little loop-de-loop thing like that. Okay, well, that's great. But you know what? It doesn't really help me understand what's happening, okay? Before we leave parametric though, I did want to also show you this thing I call ball and chain. I got that from my friend, Mrs. Gibson, who used to teach at Lake Forest High School. Okay, so if you go over to this left part of the y equals, there's a symbol that looks like a little line and a circle. And what's great about that symbol is that it traces through the graph. So if my window settings had gone to, let's say, 4 pi instead of just 2 pi, look at what happens. Right, that traced it twice. Now, if I didn't have that little dot showing me the tracing, I would just see the same static picture, and I wouldn't necessarily know that the graph had traced twice. So that's a little like thing I wanted to show you, that little like ball with a little line behind it. I think is kind of nice, okay? To solve the problem that we're actually on though, I don't want to be in parametric mode. And this is something that students often forget. Just because the question is parametric doesn't mean you necessarily want to solve it in a parametric way. Right now, what we're looking for is where this red equation is positive. And that's a question about a function. Is this function positive? Is this function negative? So I'm just going to come here to regular function mode. And I'm going to look at my window and think, okay, well, my independent variable is t, or time. So I'm going to start from time being 0, because that makes sense in context. And because it's trig-based, I'm going to go to 2 pi. I think that's going to be useful. And then I'm going to look here at my graph and see what's up. Okay, so I can see that my graph is in positive land here. And if I thought ahead, I would have remembered that this amplitude was 6. I only went to 5. So it's cutting off a little bit. That actually bothers me. I'm going to change it. Sorry. You can still do the problem without this. That's why I'm apologizing for the quick second I'm taking on this. But you can see that this graph is in positive land through here. It's in positive land through here. And it's in positive land through there. Now, if I wanted to be really fancy with my calculator, instead of having this count by ones, I would have it count by something pi related. Maybe pi over 6 would be a good tick mark. Taking really quite a long time on this. And so we just want to look at what intervals have it go into positive land and see how these are landing on those nice tick marks now. So this is pi over 3, right? This is pi over 6. So this is pi over 3. So 1 pi over 6, 2 pi over 6, 3 pi over 6. This is 4 pi over 6, so that's 2 pi over 3. So from pi over 3 to 2 pi over 3, I'm in positive land. Then this would have to be from pi to 4 pi over 3, right? So I could do this using my calculator, being smart about what intervals I pick. I could do the other question in the same manner, right? Just look for where the graph of 2 cosine of t is positive. And I just wanted to make sure you also knew about the calculate menu. So if ever I'm not quite sure if I have the right location, I could use the calculate menu and that tool that says value. And I could say, all right, I think this spot here is pi over 3. I'm not really sure. Let me find out by typing in pi over 3. And it confirms for me that that intercept there is indeed, it's an intercept because it hit 0. So that point is my pi over 3, and then this is my 2 pi over 3, and so on. So I can figure that out using the tools that are there, okay? And I'd like to come back and actually look at this parametric graph one more time. And I want you to think about that motion to the right and that motion that is up, okay? So watch how it graphs out. Okay, so the path went like this, up, then coming down, then here, coming back up, right? Like that was the motion. And we went left, then here we turned to the right, here we turned to the left, here we turned to the right, left, right. So you should be able to kind of confirm your answers as well by looking at the parametric graph and seeing if your answers make sense. Always a good thing to confirm. Logic. All right, there are a couple questions that I'd like you to try if you can find this page. And there is some extra practice in your packet. I think I included the key. So while I pause this and you try number 11 and 12, I'm going to make sure that you have the key. Let me make sure of that. I was crazy there. All right, not numbers 11 and 12. There isn't an 11 and 12. This is on pages 11 and 12, depending what page labels you're using. So this is a worksheet actually from my friend Ruth Dover, who teaches at IMSA. And there aren't actually, there's not a key included in your packet right now. but there's a key included in these slides. So what I'm going to tell you is, if you would like to do some additional practice from this set of problems, just a few problems, I am going to include at the end of this video scrolling through an answer key. So if you would like to do more practice, you can always come back to this video and just fast forward to the end and then take a look at the answers that I'm about to scroll through. Okay, if you feel confident and you don't really want to do more practice, you need to do, your French homework or whatever, practice the piano, go do that. All right, but here are the answers for this last part, okay, of the extra practice. And I'm just going to scroll through. The notation here just means range for X, range for Y. Don't worry too very much about the sketching. I haven't seen that on the AP test for years. You could use your calculator to help you. Okay, I don't have anything else for you. If you need those answers more, you can definitely rewind, fast forward as needed. Thank you for learning about first order derivatives in parametric. Thanks.